Welcome to the third lecture on Module 2 of the course Introduction to Mobile Robotics. Today we will see the different types of internal sensor that is being used for mobile robots. First is the wheel encoders. Wheel encoders are essentially sensing devices used in mobile robotics to measure the rotation of a robot's wheel. By converting mechanical motion into electrical signals, wheel encoders enable a robot to estimate distance traveled, speed, and direction of motion. These measurements form the basis of odometry, which allows a robot to track its position over time without relying on external references. In mobile robots, wheel encoders play a crucial role in navigation, motion control, and feedback system. They provide real-time data that is used by the robot's controller to regulate motor speed, ensure accurate movement, and execute precise maneuvers. Without wheel encoders, reliable autonomous movement would be extremely difficult, especially in indoor or GPS denied environment. The figure shows the different internal parts of a wheel encoder, where it consists of a motor, a Hall encoder, inertial measurement unit, where it will be measuring the angle of rotation of each of the wheels. Next, we'll see the working principle of wheel encoders. The working is similar to that of the other encoders we had seen in our previous courses. A wheel encoder operates by detecting the rotation of an encoder disk attached to a wheel or a motor shaft. The disk contains evenly spaced slots or markings. As a wheel rotates, these markings pass through a sensing mechanism, which is commonly an optical, a magnetic, or mechanical, which generates a series of electrical pulses. Each pulse corresponds to a smaller angular moment of the wheel. By counting the number of pulses, the controller can calculate the wheel's angular displacement. Using the wheel radius, this angular displacement is converted into linear distance traveled. The rate at which the pulses are generated provides information about wheel speed, while the sequence of pulses in quadrature encoders indicates the direction of rotation. The figure shows the arrangement of a wheel encoder, which is the internal thing. So we have a as already mentioned, there is an LED, we have a lens, and we can see the code wheel which is being rotated, a code wheel which will be rotating, and as each of the slots passes through the light, there are two photo sensors that is being measured. Based on the light passed, it will be detected by the photo sensor and waveforms will be generated. Next, we'll see the type of wheel encoders. Wheel encoders used in mobile robotics are broadly classified into incremental encoders and absolute encoders. Incremental encoders generate pulses as the wheels rotate and measure relative motion. They are simple, cost effective, and widely used in educational and research robots. However, they lose position information when power is switched off. Absolute encoders, on the other hand, provide a unique digital code for each wheel position. This allows the robot to know the exact wheel position even after the power loss. Although more accurate, absolute encoders are more complex and expensive. Based on sensing technology, encoders may be optical, magnetic, or mechanical. The choice depends on the application requirements such as accuracy, environment, and budget. The figure shows the different types of wheel encoders, where one is incremental and the other one is absolute. And you can see the difference in the disc plate with the number of slots more for, or the shape of the slots is different in the case of incremental encoders, and that for absolute it is different. Now we'll see what is the role of a wheel encoders in mobile navigation. Wheel encoders are fundamental to odometry based navigation. A robot estimates its position by integrating wheel motion over time. In differential drive robots, encoder data from the left and the right wheel is used to compute linear displacement and angular rotation, enabling the robot to track the path. Encoders also provide feedback for closed loop motor control, allowing precise speed regulation and smooth motion. This feedback improves trajectory tracking, reduces drift, and enhances repeatability. Encoder data is often fused with other sensors such as IMU, that is the inertial measurement unit, LIDAR, or cameras to improve localization accuracy and compensate for errors like wheel slip. Now we'll see the limitations and the practical challenges of wheel encoders. The first limitation is the wheel slippage. That, that is, it causes in the uneven terrain and mechanical wear can introduce significant errors in position estimation. Since odometry relies on cumulative measurements, even small errors can accumulate over time leading to odometry drift. Environmental factors such as dust, vibration, and temperature variation can also affect encoder performance, especially in optical encoders. To overcome these challenges, modern mobile robots combine encoder data with sensor fusion techniques and periodic external corrections. Understanding these limitations is crucial for designing robust and reliable mobile robotic systems. Next, we will see the another type of sensors that is used for internal measurements. That is the heading sensors. Heading sensors are critical components in mobile robotic system which is used to determine the orientation or the direction of a robot with respect to a reference frame, usually the Earth's magnetic north or an inertial frame. The heading, often expressed as an angle, indicates where the robot is facing and is essential for navigation, path planning, and control. In mobile robotics, accurate heading information allows the robot to maintain a desired direction, execute turns precisely, and follow predefined trajectories. Unlike wheel encoders, which estimate motion based on wheel rotation, heading sensors directly provide orientation information, making them indispensable for correcting bidirectional drift and improving overall localization accuracy. Heading sensors. We'll see the working of the heading sensors. Heading sensors operate based on different physical principles depending on their type. Magnetic based heading sensors detect the Earth's magnetic field and calculate orientation relative to magnetic north. These sensors typically measure magnetic field components along multiple axes to compute the heading angle. Inertial based heading sensors such as gyroscopes measure angular velocity around an axis. By integrating angular velocity over time, the robot's change in orientation is obtained. However, integration errors can accumulate leading to drift. To overcome this, modern systems combine magnetometers and gyroscopes within an inertial measurement unit, using sensor fusion algorithms to provide stable and reliable heading estimate. Figure shows the arrangement of a gyroscope frame, and the bottom figure shows the different parts of the different blocks in a IMU preprocessing unit. Types of heading sensors. Heading sensors used in mobile robots can be broadly classified into magnetometers, gyroscopes, and inertial measurement units. Magnetometers act as electronic compasses and are simple, low cost, and suitable for indoor robots. But they are sensitive to magnetic disturbances from nearby metals and electronics. Gyroscopes provide high short-term accuracy, and are excellent for detecting rapid orientation changes. However, they suffer from drift over time. IMUs combine magnetometers, gyroscopes, and accelerometers to leverage the strength of each sensor. This combination enables more accurate and robust heading estimation, making IMUs the most commonly used heading sensors in modern autonomous mobile robots. Next, we will see the role of heading sensors. Heading sensors play a vital role in navigation, localization, and closed loop control of mobile robots. They enable the robot to maintain a fixed orientation while moving, perform accurate turns, and align itself with goal or landmarks. In part, following task, heading feedback ensures that the robot does not deviate from the desired trajectory. In advanced robotic system, heading sensor data is combined with wheel encoder information to improve odometry accuracy. This fusion helps compensate for wheel slip and uneven terrain. Heading sensors are also crucial in autonomous systems such as AGVs, drones, and service robots, where stable orientation control is mandatory for safe and efficient operation. Now we'll see the limitations and the practical challenges. Despite their advantages, heading sensors face several practical challenges. Magnetometers are highly susceptible to magnetic interference, which can cause significant heading errors in indoor or industrial environments. Gyroscopes, while accurate in the short term, accumulate errors over time due to bias and noise, leading to orientation drift. To address these limitations, robots employ sensor calibration, filtering techniques, and sensor fusion algorithms such as complementary or Kalman filters. Understanding these challenges is essential for selecting the appropriate heading sensor and designing reliable mobile robotic navigation systems. Next type of internal sensor is accelerometer. An accelerometer is a sensor used to measure linear acceleration, which is the rate of change of velocity of an object. In mobile robotics and instrumentation system, accelerometers are widely used to detect motion, tilt, vibration, and orientation with respect to gravity. The output of an accelerometer is typically proportional to acceleration along one or more axes. We'll see the working principle. Most modern accelerometers are MEMS based. MEMS means micro electromechanical systems. They consist of a tiny proof mass suspended by micro springs inside a silicon structure. When the sensor experiences acceleration, the proof mass is displaced. This displacement is converted into an electrical signal using capacitive, piezoresistive, or piezoelectric sensing techniques. In capacitive MEMS accelerometers, acceleration changes the distance between the capacitor plates, resulting in a measurable change in capacitance. This change is proposed by on-chip electrons to produce an acceleration value. Types of accelerometers. Accelerometers are classified based on their sensing mechanism. Capacitive accelerometers, high sensitivity and low power consumption, commonly used in mobile robots and consumer electronics. Piezoresistive accelerometers, suitable for high G applications but less sensitive at low accelerations. Piezoelectric accelerometers, ideal for vibration and shock measurement, but cannot measure static acceleration. They are categorized by the number of axes measured, single axis, dual axis, and tri-axis accelerometers. Now we'll see the applications. In mobile robots, accelerometers are used to detect linear motion and sudden acceleration estimate, tilt, and inclination using gravity. Assist in dead reckoning and navigation. Improve orientation estimation when fused with gyroscope and magnetometer data in an IMU. They are especially useful for detecting terrain changes, collisions, and dynamic moments. What are the limitations of accelerometers? Although accelerometers are versatile, they have limitations. Noise, bias, and temperature variations can affect accuracy. When the acceleration data is integrated to obtain velocity or position, errors accumulate over time, leading to drift. Therefore, accelerometers are typically used in combination with other sensors such as gyroscopes and wheel encoders. Inertial measurement units. An inertial measurement unit is an integrated sensor module that measures a system's motion and orientation in space. It does this by combining multiple inertial sensors, primarily accelerometers and gyroscopes, and often a magnetometer to provide real-time estimates of acceleration, angular velocity, and heading. Core components of an IMU. Accelerometer measure linear acceleration along the x, y, and z axis. It can also sense gravity, which allows estimation of tilt, that is, the pitch and roll, when the system is stationary or moving slowly. Next is a gyroscope. Measures angular velocity about each axis. By integrating angular velocity over time, the system determines the change in orientation. Gyroscopes are accurate over short duration but suffer from drift over time. Magnetometer, optional but it is not common. Magnetometer, optional but common, measures the Earth's magnetic field to provide an absolute heading reference, similar to a digital compass. It helps correct long-term drift from the gyroscope. Working principle. An IMU continuously samples data from its inertial sensors. Accelerometer. Data provides information on linear motion and gravity direction. Gyroscope data captures rapid rotational changes. Magnetometer data offers an absolute directional reference. These sensor outputs are combined using sensor fusion algorithms such as complementary filters or Kalman filters to produce stable and accurate estimates of roll, pitch, and yaw. Sensor fusion exploits the strength of each sensor while minimizing their individual weakness. Role of IMUs in mobile robotics. In mobile robots, IMU are essential for heading and orientation estimation, improving the odometry accuracy when fused with wheel encoders, maintaining the stability during turns and uneven terrain, enabling navigation in GPS-denied environments. IMUs are widely used in autonomous mobile robots, drones, AGVs, and humanoid robots, where reliable motion sensing is critical for safe and precise operation. Limitations. Despite their importance, IMU face practical challenges. Gyroscope drift causes orientation errors over time. Accelerometer noise affect motion estimation. Magnetic interference can cause distort magnetometer, leading to overcome these issues. IMUs are carefully calibrated and combined with other sensors such as wheel encoders, GPS, LIDAR, or vision system.